On this episode, we'll teach you in easy-to-follow steps how to build a cruise ship,
Pop all the rooms in the place like Lego.
a pipe organ,
The entire building is a musical instrument.
and your very own Apache helicopter.
I wish I could shoot one.
Instructions are coming, so take notes. And we'll show you how to build everything.
40, take one, common mark, soft sticks.
When I think about a cruise ship, it's essentially a huge skyscraper just on its side, floating in the ocean, full of people, ready to eat a lot.
How to build a cruise ship.
Cruise ships of today are absolutely modern marvels.
The scale of these things is incredible. I mean, these are literally floating cities. We're talking Broadway shows, multiple restaurants,
Buffets, shrimp, Mai Tais,
cocktail bars, bowling alleys.
too many margaritas.
A cruise ship can house as many as 8,000 people at once. That is a larger population than some small towns in America.
To build your own 20-story cruise ship, you will need 150 miles of pipes, 3,300 miles of electrical cables, 158,503 gallons of paint, 500,000 individual steel parts, and 1 bottle of champagne. Cost to build $1.4 billion plus shipping. Step 1, start at the bottom and work your way up.
For many centuries, ships have been built from the keel up, and that's the best way to build a ship, right? You build it down its back where it needs to be the strongest.
So when you build a car, it goes down an assembly line, and there's workers at every point in the car passes, and they work on it. But when you're building a cruise ship has to stay in one place, so all the workers are the ones moving all the way around it.
Just building them requires so much space. We're literally talking 5 football fields. So you think about that distance, it's just incredible.
Step 2, install prefabricated components.
The fundamental approaches is that they try to assemble as much off-site as possible. The components arrive basically in modules. So you've got each of those different staterooms arriving sort of mostly pre-built.
All the 1,000+ rooms of this ship all have everything already in place, because otherwise the workers couldn't build it. They make those hallways so tiny so they can fit more rooms, so they just pop all the rooms in the place like Lego.
In order to build your modules, start with sheets of high-strength steel, up to 39 feet long and 1 inch thick. Cut steel sheets using plasma, laser, or oxyacetylene equipment, sold separately. Weld the metal together into 3-dimensional cubes. These are the building blocks which become the hull and cabins of your cruise ship.
They weld them together in box patterns to increase the strength by up to 4 times.
The extra strength of box-shaped modules can be demonstrated in our test laboratory. On its own, this flat, 1/4-inch thick board is unable to bear the weight of a 28-pound cinder block. But when 4 of the same boards are fastened together as a hollow 3-dimensional box, the load-bearing capacity is quadrupled. By the time you have affixed all your prefabricated components, your cruise ship will weigh over 200,000 tons. But don't worry, it won't sink, thanks to buoyancy.
Cruise ships look like marvels of engineering because they are. You can take this thing that's 1,000,000 pounds or more, and it floats.
It's one of those weird things you look at, and in your brain, you're like, this shouldn't work. But because of science, it does.
The Archimedes principle says that an object will float if it weighs less than the amount of water that it displaces. So it's really about density. Something like a bowling ball will sink because it weighs more than the amount of water that takes up the same amount of space.
It's the buoyancy principle. That water is going to cause a force called the buoyant force to push back up. That's why it's a beach ball isn't very heavy, but it's really hard to pull under the water, right? That's because it's moving a lot more water out of the way than what it weighs, and that's why a cruise ship stays afloat.
The ship is made of a lot of metal, which is very heavy, but there's also a lot of air in all the rooms. So on the whole, the ship weighs less than a ship's worth of water, so it floats.
But it is kind of a comfort to know that no matter how much you eat on a cruise ship, like, you're not going to sink that thing. It's not going down.
Now that your vessel can float, you must give it the power to move. Step 3, get your cruise ship cruising.
Modern cruise ships use a diesel-electric process to produce their propulsion. They use a diesel engine to drive an electric generator. And then the electricity that's generated drives electric motors, which are connected directly to the propellers.
Modern propellers are designed slightly different from the way that they used to do it before. Cruise ships use what are called azimuth thrusters, which are giant propellers inside of pods. The azimuth thruster replaces a rudder and a propeller system in one, and they work just like rudders, allowing the ship to turn on a dime. If the Titanic had azimuth thrusters, which definitely it did not, there's a chance that it may have been able to avoid the iceberg because it would have been able to maneuver and evade a little bit better.
Just imagining it in my head.
Build an azimuth thruster with a 200-ton bronze propeller and 30-foot-long pod.
Bronze is a pretty ideal metal for saltwater. It's resistant to corrosion and also resistant to bending and breaking.
Be sure to follow all instructions. Do not over-tighten. When finished, your azimuth thruster should look like this.
The way propellers work is that as they turn, they generate a difference in pressure behind and in front of the propellers. This accelerates the water back, which is what propels the ship forward. The propellers on a cruise ship move much more slowly than the propellers on an airplane because water is so much more dense than air.
There's a point at which a propeller can move too quickly through water, and it becomes inefficient. Modern cruise ships actually get a better transfer of energy by using slower, rotating propellers and higher-pitched blades.
Step 4. You're ready to set sail. It's time to launch your ship on her maiden voyage. Commemorate by breaking a bottle of champagne, A. Overhaul, B. Bon voyage. Coming up next.
The Apache helicopter has to be one of the most badass war tools ever made.
Watch out, bad guys. It's like riding on the neck of a flying triceratops, a giant metal beast, a flying mechanical dragon. No.
How to build an Apache helicopter.
It is the most capable attack helicopter in the world.
This thing coming at you with those rockets, it just looks like a giant angry wasp. Let me tell you something. If your neighbors are annoying, get an Apache.
You will be building a Boeing AH-64 Apache attack helicopter. And for this, you will need 1 aluminum fuselage shell, video, infrared, and thermal imaging systems, bulletproof armor, bulletproof rotor blades, 2 1,800 horsepower turbine jet engines, 38 rockets, 8 missiles, and a cannon, and around $52 million. Follow instructions carefully. If you screw up, it's a long way down. Step 1. Begin with the fuselage.
You start off with a hull that's made out of aluminum. Aluminum is lightweight, which makes the Apache faster and easier to maneuver. And you line it with ballistic foam so that any possible projectiles that pierce that aluminum get captured in the ballistic foam. But as if that isn't enough, you add a layer of resin to keep those incoming projectiles from being able to catch fire. And then you add layers of Kevlar, which is a synthetic fabric made up of chains of strongly bonded molecules. Kevlar is able to stop bullets by spreading their energy laterally. You sandwich all those things together, and you've got basically bulletproof to the next level.
Step 2. Assemble engines. Insert engine number 1 into left engine bay. Secure with supplied bolts. Attach classified stealth technology. Repeat process on other side with second engine.
So the Apache has 2 General Electric 1,800 horsepower turbine jet engines. That's basically $500,000 worth of horsepower in this guy. Suck, bang, blow is what they say. It sucks in gas, it heats it up, and it kicks it out.
Suck, bang, blow. Sounds really dirty, doesn't it?
Hey, keep it clean.
The Apache is one of the fastest helicopters out there. Top speed of 200 miles an hour, which is no small feat for a helicopter. Like, just instant on kind of performance.
The strength of these engines is pivotal to the kick-assness of the Apache. That's not a term. You want to try that one again simpler?
No. Now, the problem with the jet engine on a helicopter is there's a lot of heat, which gives a heat signature, which your enemy can use a heat-seeking missile. The Apache has a secret system to draw in cold air, mix it with the jet turbine exhaust, and cool it so, in effect, a heat-seeking missile can't find it.
Now give your helicopter the ability to fly. Bolt load-bearing struts into fuselage. Insert rotor shaft through center of struts. Attach titanium-encased bullet-resistant rotor blades, A through D, to swash plate.
The swash plate is what allows the main rotor to move. It's a plate that lets the rotor move forward, back, left, and right.
It's incredibly maneuverable. It can flip upside down at good altitudes.
Some of the moves that the Apache helicopter makes, if you tried to do in a normal helicopter, the forces would rip the rotor apart.
I mean, they can handle pretty much anything. Super cool. Not gonna lie.
Step 4. Add a small part that makes a big difference. Attach tail rotors, A and B, to tail assembly. Now it's looking like a helicopter.
If you've ever watched a movie and seen where the tail rotor gets shot out on a helicopter, you notice that the entire body starts to spin. This happens because every force has to have an equal and opposite force.
Because the helicopter isn't fixed to anything, as the main rotor turns one direction, it would make the Apache turn in the opposite direction. But the tail rotor opposes the motion. And when the forces are balanced, the Apache flies straight.
The Apache helicopter
seats in a helicopter. If you're going to take two pilots and a multi-million-dollar aircraft and put it in a combat zone where people are shooting at it, you need some redundancy.